Welcome back to my YouTube channel. Today we're going to be talking about really two major reactions for organic chemistry called the Aldol reaction and the Michael addition reaction. As you can see, the way I want to structure the video is I want to talk about 4 of the main compounds involved with these two reactions, as well as give you a general idea of how those general reactions look, as in what their starting reagents are and what their end products are. And then from there, I'm going to go in the series of aldol first, aldol second, aldol condensation third, and Michael addition fourth, in that order. One thing I want to note also is that the aldol and Michael addition reaction aren't two completely separate reactions. They are intertwined in the sense that a product of the aldol condensation reaction, which aldol condensation is kind of like a subset reaction of the greater aldol reaction. The product of the aldol condensation is a reagent in the Michael addition reaction. However, to be fair, this product that we're going to use from aldol condensation as a reagent in Michael addition is and can be synthesized through various other means. This is just one means by which it can be made, and I wanted to cover these two specifically also just for the simple fact that aldol and Michael addition are two really big core ideas. So first, let's just look at these 4 compounds. These are the 4 compounds that are aldol, alpha beta unsaturated carbonyl, it's kind of hard to read, the enolate ion, and a dicarbonyl. These are really crucial to these. They're going to be intermediates as well as reagents and products. So first, the aldol. What is the aldol? As you can see here, the aldol is any molecule where there is a carbonyl here, and there is a carbon separating a hydroxyl or alcohol group. That's all it is. And one thing I want to know also with this is the way that we classify what these 2 carbons and their respective hydrogens attached to these carbons are. So we think about this in terms of, here's the carbonyl, this is the carbon, this is the oxygen, they're double bonded to it. That's the carbonyl. The way we think about it is that this carbon here and this carbon here are both alpha carbons, and any hydrogen attached to that alpha carbon is also an alpha hydrogen. Furthermore, any carbon and or its hydrogen that's adjacent to the alpha hydrogen is called the beta carbon or the beta hydrogen. And we use this just as a way of specifying what parts of the molecule is what, and just to keep track of everything is going. And so second, this is the alpha beta unsaturated carbonyl. So let's talk about what the name means in relation to what it actually is. So first, what it actually is. It's just, again, a carbonyl, and then here we have a double bond right next to the carbonyl. And so the meaning behind the name is obviously carbonyl indicates the carbonyl, and the alpha beta, like I said before, this is the carbon of focus, this is an alpha, and this is a beta carbon, looking on this right side. So the name comes from the fact that this alpha and beta are both unsaturated, meaning unsaturated of hydrogen, therefore, and they're still neutral, therefore either they're going to be substituted something other than hydrogen, or there's going to be a double bond between them in order to make it still neutral by having 4 connections to, so 4 things to be neutral, because carbon has to be connected to 4 things to be neutral, otherwise it's not neutral, it's an ion. And so again, it can mean either of those things, but in this case what we mean by alpha beta unsaturated is that in place of the unsaturation the hydrogens, instead there's going to be a pi or a double bond here to render it neutral. Thirdly, we have the enolate ion. The enolate ion exists in really 2 sort of resonance structures, and of course the actual molecular structure of the actual compound is a hybrid of these 2, so it's kind of like half and half in a sense, sort of half and half. So as you can see, it exists really in 2 forms of resonance. This one, you see there's a carbonyl here, a normal carbonyl, and then this alpha hydrogen, or alpha carbon, sorry, is negatively charged. Or it could also be the opposite, where there's a double bond in place here and the oxygen is negatively charged. And then lastly, we have a dicarbonyl. These are 2 separate molecules, by the way. I could probably draw a line here. A dicarbonyl, hence the name, is just any compound with 2 carbon or 2 carbonyls. Here we have one here, and there's a carbon here. This is the alpha in between them. It's also the hydrogen that's attached to this carbon, this alpha carbon, is also extremely acidic due to the fact that the oxygens are very highly electronegative. Therefore, electron density is going in this net direction towards the oxygens, away from this center point. So it would, because of that, because of its location relative to these two carbonyls, it readily loses hydrogen protons. So it's very likely to lose hydrogens there. So let's look at this. So here's the reactions. These are all the compounds that are going to be the major players involved in these reactions. So now let's look at the actual reactions themselves. So first we have the aldol reaction. So let me say something first. So this is the basic simple aldol reaction, and these two, the retroaldol and aldol condensation, as well as something else I didn't write here called aldol cyclization, are kind of like off branches of this major aldol reaction. They all kind of come from, in a way, from this initial reaction. And then Michael addition is something more separate, but it's still somewhat intertwined. So as you can see, what we start off with is an aldehyde or a ketone. In this case, we also have sodium hydroxide. Really, when we say the sodium hydroxide and the presence of water, when we say sodium hydroxide, what we really refer to is the hydroxide ions that come from it when they separate in the presence of water. And really, I didn't write it here, but we're going to talk about this in a second, but really what's actually happening is not only is it just this carbonyl reacting with hydroxide ions and water, there's also it reacting with its parent compound. So in other words, it's like this thing here will change in reaction to the hydroxide ions to produce something that's negatively charged at one place, the enolate ion, and then this enolate ion is actually going to react with a parent compound, or in the case if it's a crossed aldol reaction, it will react with something that's not actually the parent reaction, in which case you would have something different reacting with it, with the enolate ion that you get from this after it was deprotonated, in which case you can get a variety of products. That's called the cross aldol reaction. The idea of it is that you have multiple different reagents acting to form probably 4 different combinations of products. We'll talk about that in a second. But the idea is that this aldol reaction yields an aldol. An aldol is just simply, like we said before, we already covered that. So retroaldol is basically this idea that the aldol reaction is reversible. It can go in the forward and reverse process. And retroaldol is basically the same thing as the aldol, just in reverse, starting from the product to the reagents, and you do everything backwards to get the reagents. And like I said before, I didn't write here, but really we have 2 of these, like 2 carbonyls reacting with each other in combination with these things. And so this shows just what I mean by that with the retroaldol reaction. This is the starting, this is the ending, and in this case, this is starting, this is the ending, just forwards and backwards. Aldol condensation. Aldol condensation has to do with what you do after the aldol reaction. So if you do the aldol reaction and then you also heat the reaction mixture up to a certain temperature, what actually happens is that you have the loss of water, and so that's really what that is. But it produces the alpha, beta, and unsaturated carbonyl, which is a significant player. And lastly, the Michael addition reaction. Michael addition reaction is just the idea that you have a dicarbonyl, or it doesn't necessarily have to be a dicarbonyl, plus an alpha, beta, unsaturated carbonyl, or it could be something similar to it, and the presence of water and acidic protons. And basically what just happens is that these two are going to combine in this case, they're going to combine to form one larger product, a neutral product. And in this case, they would combine at this alpha carbon point right here. Again, it's between these two. Combining in the micro addition reaction, it will combine at this beta carbon point right there. This would be the alpha position, this would be the beta. In a major reaction, it would go here, but in this micro reaction, the Michael addition reaction, it's going to go right there. So let's look firstly at the aldol reaction. So here, again, this is the general form. The reason why the starting reagent and the general form, which is this, versus the specific mechanism looks a little different is because here we kind of wrote out what we mean by here. Here we kind of have to imagine that there's 3 hydrogens attached to this carbon, this point right here. And so here we actually explicitly wrote it out. Here it's implicitly applied. Here it's explicitly shown. So the first thing that happens is that hydroxide ions from sodium hydroxide is going to deprotonate an alpha carbon of the carbonyl, one of the hydrogens, producing an enolate ion. Like I said before, the enolate ion resists in resonance. However, here I've only drawn this form of resonance structure because it is the one that's important for the next step, which is the next step is that you have a parent compound which would be the original, another of the original compound that's unaffected, or if it's cross-aldol, you'd have something else that's different, that's not actually the exact same of the original. And what essentially just happens is that these two are going to combine at, it's going to combine again in this resonance structure at this negatively charged carbon, is going to combine there at that carbon attached to the double bonded to the oxygen. So what you essentially get is this right here. This is the next to last step. The only problem with this next to last step is you realize that it's not perfect. It's not the aldol because it's missing a hydrogen right there because it's was singularly negatively charged oxygen. So what happens last is that water will act as an acid, and it will essentially just protonate that negatively charged oxygen, yielding the aldol product. And then this here is just to show that the retro-aldol reaction, it really is just the reverse. It does everything that you did here backwards. Next up, we have, so this is, I think I mentioned this. This is a aldol condensation reaction. So what you start off with is an aldol. This is the same thing we got from the general reaction simple for aldol. It's the carbonyl and then a hydroxide group adjacent to the carbonyl. What happens first is, again, it's not written here. There's no hydrogens written here, or here, sorry. But you have to basically imply that there's two hydrogens right here, because again, carbon has the 4 bonds. At this point, if you don't draw the hydrogens, it's only bonded to 2 things. Therefore, you need 2 more things to bond with, and then you would assume that it's hydrogen. So that's why I wrote it out here, but not here. And so the hydroxide ion is going to deprotonate one of these alpha hydrogens at this point. And then what you end up with, of course, is a negatively charged carbon here. And so it rearranges itself to lose the alcohol group, so that it's now neutrally charged. So as you can see, the negatively charged here goes to forms a pi bond between these 2 carbons, and this carbon right here, the beta carbon, relative to the carbonyl, loses the alcohol group. So overall, you lost a hydrogen here, and you lost an oxygen hydrogen here. Therefore, the overall net yield would actually, you would lose a water total. This is, I forgot to include this. This is an aldol cyclization reaction. Very simply, here you have a dicarbonyl. They have to be relative to each other, 1 and 5 or 1 and 4. So you have to have like, what, 2 or 3 carbons in between. In this case, they're relative 1 and 4 to each other, and they have 2 carbons in between each other, in between the 2 carbonyls, I mean. And what essentially happens in the presence of sodium hydroxide and ethyl alcohol, the ethyl alcohol being the ET, that's ethyl, stands for ethyl, and OH is alcohol, it will form a cyclic product. It'll be like in this case, this is what, 1, 2, 3, 4, 5. This is a 5-membered ring. It can form a 6-membered ring or 7-membered ring, so on and so forth. And again, where it attaches here, you have a double bond and you lose a carbonyl, and everything else more or less remains the same. You can see that the numbering of it tracks where everything is kind of like going. Okay. Excuse me. So last but not least, we're going to talk about the Michael addition reaction, which is this one right here. This is the last one. So one of the things I want to point out is that the Michael addition reaction, as shown here, the general mechanism, it includes these 2. This is a dicarbonyl. This is a alpha beta unsaturated carbonyl, to yield the addition product of both of those. And here I use these 2 specific compounds. Really, you could use a variety of them. I only use these 2 just because I feel like it. And so what we really mean by these 2 compounds is that this, what we would say, is the Michael donor. This is the Michael acceptor. What actually happens is this will become the nucleophile, this will become the electrophile, and this will have a negative charge, and then when it moves over, everything will move over to make it work. And so again, it all follows the same general pattern. There's a negatively charged here in between electron withdrawing groups for the Michael donor, and for the Michael acceptor, you have usually just a double pi bond adjacent to a carbonyl or electron withdrawing group otherwise. So let us look at the actual reaction. So first, like I said, there needs to be a negative charge in between these two carbonyls. And so the way we do that, in order to react further later on, in order to get this negative charge here, of course, naturally, it doesn't have the negative charge. So to get there, we just have to react it with the base, a hydroxide ion, so that it removes one of the hydrogens. Another thing I want to point out, again, I think I reference it, is that this hydrogen is going to be extremely acidic because it's between two carbonyls, two electron withdrawing groups, meaning the electron density is going to go and just away from this. So after you do that, you get this negative charge here, and then you have the alpha beta unsaturated carbonyl. Again, this is the product of this reagent, and this reaction is the product of the aldol condensation reaction. You can get it a few other means. So they're going to attach here at this point, at the negative charge, the alpha carbon at the beta carbon point of this. This is a microreaction. It could attach here and do it a little differently, but in this case it would here. And so the way that it's going to be able to attach here also is that you have to have this pi bond move over, and to have this double bond between the carbon and the oxygen move over to produce a negatively charged oxygen to make way for it. And as you'll see, this is the next last step. The reason why it's the next last step and it's not the last step is because we have a negatively charged oxygen here, we have a double bond here, and so essentially in order to fix that, we will have water. This is reacting in the presence of water, and water will donate a proton. It will act as an acid, and this is what the air is signified. And as you can see, with water adding to it, the negative charged oxygen can now make way for a double bond there in place of it. And so essentially the product of all of this, as you can see, is just the addition of the Michael acceptor and the Michael donor to produce one overall neutrally charged larger molecule. And yeah, I think that's it. So just to recap, here's the four major players: aldol, alpha beta unsaturated carbonyl, enolate ion, really caring about this form of it, or excuse me, this, and dicarbonyls, aldol, aldehyde. And again, I didn't talk about cross aldol, I probably should have. It yields an aldol. Retro aldol is the reverse process. Aldol condensation is what happens after the aldol reaction, and I guess in a sense also within the realms of retroaldol, because that's also happening in equilibrium. It's what happens after that when you heat it to lose water. And Michael addition is where you take a product of the aldol condensation, which you can otherwise react it with a Michael donor, and you get the addition of those two things.